There was a doubt from NPN junction regarding depletion layer and potential barrier. Look at this part. This is your depletion layer. This is P side, N side. From N side, transfer of electrons takes place, and this side becomes negative due to the transfer of holes. N side becomes positive. This gives us an electric field away from positive towards the negative charge. Away from positive and towards the negative charge. This much I had made clear in the last lecture itself. How do we form this depletion layer? And because of this, if you plot a potential versus X graph, then that graph will look like this. Let's say you start your graph from this point. And if you are drawing your V versus X starting from this position, then in the direction of electric field potential decreases, it will look like this. Potential decreases. It's our wish at what point we keep the lowest point, because you know we are not interested in potential, we are always interested in potential difference. Just to make things clear, it will look something like this. That's a graph of V versus X. Now, what does it tell you? There is no net charge in this region. There is no electric field in this region. Let's say this portion has some potential of 10 volts. And you can say that there is no electric field, then how come potential is there? And that's what I am telling you. Potential has no meaning at all. The thing which matters is potential difference. We have taken, for the understanding purpose, that this side has some potential of 10. This is giving you 10 volts. There is no electric field. It means no change in potential takes place. No change in the potential takes place. And then, in the depletion layer, because of the electric field, potential decreases. In the direction of electric field, potential decreases. Again, you move to this side, this portion. There are no charges in this portion. There is no electric field. And therefore, your potential remains what? Same. This width is your potential barrier. This is delta V. From here to here, this is called your potential barrier. This is something which I explained in the last class itself. Now the doubt was that once you connect a battery, let's say in positive bias, in forward bias like this, which makes this terminal positive and this terminal negative. Now, the doubt is that once you make this terminal positive, this terminal negative, there will be a net electric field in this direction. That's what the doubt is. There will be a net electric field in this direction. Well, that's not the case, first of all. There is no net electric field because of this plus and minus, because if you remember the way we plotted VI characteristic graph for a diode, the graph looks like this. This is your V, this is your I, and the shape of the graph is this. Let's talk about forward bias because now it is in the forward bias region. If you want me to discuss the reverse bias also, you can use the same concept. But let's focus on the forward bias part. What is this? This I told you for silicon. This is around 0.7, 0.6 volts. What is V? V is the potential difference. V is the potential difference of the external source. Now, if I remove the battery, if you remove the external source, this is the depletion layer. Now, what is happening at this moment? At this moment, only those holes which are highly energetic. Remember, there is no battery connected. Only those holes which are highly energetic. Highly energetic means those holes which can overcome this electric field produced in the depletion layer. Only those holes which can take care of this electric field can move from P region to N region. And when it does, simultaneously a drift process takes place. What is that drift process? Due to thermal collisions, I have told you that everywhere covalent bonds, they break, you create a pair of hole and an electron. Those holes and electron which you create in the depletion layer because of thermal collisions, they move because of this electric field. Suppose you create a hole in this region, in the depletion layer, then this hole is going to move in this direction because of the electric field. This hole, when it moves, it gives us drift current. This hole, when it moves, gives us diffusion current. Now, no battery is connected, only highly energetic holes are moving from P to N. At the same time, very highly energetic holes, they move from this position to this position, P to N. Now, as they move from P to N, you get diffusion current, but at thermal equilibrium or at steady state, This diffusion current is being balanced by the drift current. Thermal collisions, they produce these holes, at the same time electrons also. Let's just focus on the holes part first. These holes, they start moving from this position to this position. This movement of holes is cancelling this movement of holes at equilibrium, at thermal equilibrium, at steady state. Now, these are those holes which can only overcome this electric field. There are holes which are having less kinetic energy, they cannot move. Therefore, if you provide an external source, this external source must not produce an electric field which can overcome this electric field. If this potential difference, an electric field produced by this potential difference, can give enough energy to those holes which earlier could not cross from P to N, then you get what? Additional diffusion current. Now try to understand the whole thing again with the numbers which I explained in the last class. I told you that, let's say there are holes with kinetic energy 9, 10, 11 and 12. These are the kinetic energies. Now, with these kinetic energies, we found that only 11 and 12, these kinetic energies, they can overcome this electric field. If only 11 and 12 can overcome this electric field, then what about 9 and 10? These 9 and 10, now if you give them little bit of extra energy, then they can also cross from P to N, which means the moment you apply a positive or forward biasing voltage, you see that little bit a small development of current. I hope you can see the graph. In the graph, the portion is a raised portion. It's not touching this, slightly above. So, the moment you increase your forward bias voltage, you find that 9 and 10, these holes, they also move and increase what? Diffusion current. And I told you in the last class itself that drift current, it does not depend upon external voltage. It remains same. It depends, this drift current, it depends basically on the temperature. If you are keeping temperature constant, then number of thermal collisions will decide hole and electron pair generation. The way you break your covalent bond, that will depend on the temperature. If you keep your temperature constant at a constant rate, this whole electron pair generation will continue. You can control diffusion current with the help of biasing voltage. Now when you do this, the moment you increase your biasing voltage, you're basically increasing kinetic energy of these holes. You don't have to overcome entire electric field. You don't have to overcome this entire electric field. A little bit of extra energy, these will move, will increase your diffusion current. There will be a net current in this direction. There will be a net current. So what happens if this was your potential barrier? When no forward biasing was present, then we say that the moment you apply this plus and this minus, because of this plus and this minus, there will be an extra electric field. Let's call it E dash. This E dash is the external. External means because of the external source. This E is the internal. Internal means because of the diffusion, because of the depletion layer, because of these charge development. So, look at the length of both arrows. I've drawn this arrow a little bit smaller than this one. That means net electric field is still in this direction. Net electric field is still in this direction. And if you draw a graph of V versus X, then what will happen? Just for the reference, next time when you draw the graph, let's draw the graph in this form. The graph will look like this. This is the new delta V. This is the old delta V. This is your new delta V. Let's call it delta V dash. This delta V dash means your potential barrier has decreased. Now, keep on increasing your external voltage. As you keep on increasing this external voltage, what happens? At 0.7 volts, you will find that your E dash and E, they both are equal. Once your E dash and E both are equal, depletion layer is gone. The moment depletion layer is gone, now there is no electric field left which can stop these holes or the other holes with less kinetic energy from moving from the side P to side N, and therefore any small increment in voltage will result in tremendous increase in the current flow. That's what is explained at 0.7. So at 0.7, remember your E dash is equal to E. It's not that the moment you apply a forward bias, at the very moment your external field should be greater than the internal electric field. No, that's what doesn't happen. I hope the question which you are asking, Shreyas, is this thing clear or not? Or if you have any other doubt, you can switch on your mic.
Yes, sir, now it is clear.
Okay. What is half-wave rectifier? Suppose you want to convert an alternating current into a DC, valid current. Now you know that alternating signal, if you represent it in this form, this is plus, this is minus, this is plus, this is minus. This is your alternating circuit. Now, look at a setup like this. A simple setup. We have an AC source and you have a transformer coil connected. To an external load. With a diode in series. Like this. This is source Vs. This is for source. Now, assuming 100% efficiency, we'll say that same potential difference and keeping same number of terms. You are interested in the concept part, basically, the way things, this how wave rectifier it works. What we are saying is that this same alternating source voltage is available to secondary source, secondary coil. This is your primary coil, this is your secondary coil. This Vs stands for source. The same source voltage is available here, but this voltage is changing with time. Vs versus T is an alternating signal. Half of the time plus, remaining half of the time negative. Now, the moment, let's say this place is T equals to 0 and this is your T by 2. This is your capital T and so on. When T is greater than 0 and less than T by 2, for T greater than or equal to 0, less than or equal to T by 2, this diode has this terminal at positive and this terminal at negative, which means your potential difference is what? Positive. This is plus, this is minus. What is happening? For this time range, greater than 0, less than T by 2, let's say this is high and this is low. High and low. If this is high, then this terminal is also high and this terminal is also low. If this is low, negative is low. This is high, positive is high. That's what the positive negative it means in this setup. Which means your circuit is in forward bias, and if it is in forward bias, you will find that a current is flowing through the resistor R. If current is present and you draw VR versus T graph, if you draw VR versus T graph, then for this time range, your graph looks like this. Peaks are not same. These peaks are not same. Your VR is basically I multiplied by R. Theme is, half of the signal appears across the resistor or external load. But the moment your time is greater than T by 2 and is less than or equal to T, this part. In this part, I'm showing the whole thing with blue color. You can also use same technique. For this time range, this high becomes low, this low becomes high. Blue with blue. This becomes low, this becomes high. Which means this becomes negative and this becomes what? Positive. This is negative, this is positive. Which means what? In this portion, for this time your diode is in reverse bias. And if it is in reverse bias and assuming an ideal diode, you will find that no current will pass through the diode and therefore through the resistor, which means there will be no potential difference, and you can show your graph like this, a graph which is touching the time axis. For the time range T by 2 to capital T, diode is in reverse bias, there is no current, there will be no potential difference from Ohm's law, IR, and therefore T by 2 to capital T, your VR becomes 0. Then again, the moment your time is in this part, T to 3T by 2. Now you can understand the same thing. From T to 3T by 2, things are exactly similar to this portion. And therefore, again, diode will be in forward bias and you will find a current like this. And because of that current, you will see a potential difference. This type of rectification is called half-wave rectification. It was an alternating current. It was alternating between plus and minus, but now it is alternating between plus 0 plus. That means there is no negative current. Current is only flowing in the same direction or it is not flowing at all. This type of rectification is called half-wave rectification. Draw the setup. If you have different colors, choose these different colors in this form. Otherwise, do whatever you can. Go down this much. Write down the statement. During first half of alternating cycle, during first half of the alternating cycle, inside bracket, T greater than 0 less than T by 2, T greater than 0 less than T by 2, PN junction diode is in forward bias, and therefore it offers no resistance, inside the bracket in ideal situation. This thing, ideally, you will say that in forward bias it doesn't offer any resistance, but I just showed you the graph and you know that you will experience a resistance equivalent to 0.7 volts. But we're not interested in that 0.7 volts. During first half of alternating cycle, PN junction diode offers no resistance and therefore a current is present, a current is present through the external load. A current is present through the external load. Inside bracket capital R. But for next half cycle, but for next half cycle, PN junction diode is in reverse bias and therefore offers infinite resistance and therefore offers infinite resistance. And because of it, no current flows through external load. Thus giving us an output, which is half rectified. That's your input and this is your output. Thus giving us an output which is half rectified. Now, these things, the way short answer questions you can expect in competitive examinations is something like this. If I ask you that peak value of, write down the question. Peak value of output voltage is V naught. Peak value of output voltage is V naught. Then find out average value of output voltage for one complete cycle. Average value of output voltage for one complete cycle. Let's see how many of you can answer this question. Peak value of output voltage is V naught and I need average of the whole thing. for one complete cycle. I'll give you a hint. For alternating current, when peak value was I naught, average for half cycle was 2 I naught upon pi. For an alternating current given by I equals to I naught sine omega t. An alternating current average, complete average, that was 0 plus and minus, but average for half cycle was 2 I naught upon pi. Now I hope you can answer the question with the help of this much hint. Good, that's what the answer is. For this much portion, your average is 2 V naught upon pi. If they ask you what is average for half, then answer is 2 V naught upon pi. But if they ask you answer for complete portion, from this to this, from this place to this place, your average will be what? This average plus this average divided by 2. That's how you calculate averages. What is average for the T by 2 to capital T part? Average for this portion is 0. There is no current. There is no voltage. Average for this portion is 2 V naught upon pi. And therefore average from this to this is 2 V naught upon pi plus 0 divided by 2. This plus this, whole thing divided by 2. What is the answer? The answer is V naught upon pi. Remember this. As a short answer question, you can expect something like this. Let's see how many of you can answer this part. What is the RMS value of voltage? RMS value of voltage, output voltage for one complete cycle. Write down the question. For a half wave rectifier, if peak voltage is V naught, then find out RMS value of voltage for one complete cycle. RMS value of voltage for one complete cycle. Try to answer this part. That's not a question of semiconductor, it's basically a question of alternating circuit. And I hope you remember how to find RMS and all these things. If you are interested in VRMS or IRMS, you go for this V dt 0 to t divided by dt 0 to t square root. Square mean root square, then the whole integration divided by dt is called mean. And finally, take a root. For a signal like this, a complete alternating signal, you know that your RMS is V naught upon root 2. Had it been a complete signal, alternating signal, then you would expect an RMS value of V naught upon root 2, which everybody knows. But in this question is, what is the RMS value when it is half wave rectified? Only 3 responses so far. First of all, if I ask you what is RMS for the first half, let's waste no time. RMS for the first half, if they ask you RMS for the first half, then that is V naught upon root 2. Same. For t greater than 0, less than t by 2, your VRMS is V naught upon root 2. It's the same thing. And if I ask you what is VRMS for t greater than t by 2 and less than t, for the next half, there is no current, there is no voltage. This thing is what? 0. These are the RMS values for first half and second half. The question is, what is RMS for complete cycle 0 to capital T? Put down this, and hopefully now with the help of this much hint, you can answer the question. Note down this much hint for first half, for second half. The question is for complete cycle. Look, let's say this value is A. Once you have found VRMS, what you can do is take this RMS value and complete the whole thing again. This is VRMS. Let's say V naught upon root 2 is what? A. And how will you use this formula? Try to understand the basic concept. Root over V square, which is A square. Now remember, it's a constant thing. When you are taking square mean, once you are taking mean, you're making things what? Constant, uniform throughout. So this is V naught upon root 2, which is a square of that dt, although it's a waste of time, but you will understand better. This is from 0 to t by 2 divided by plus the whole thing 0 t by 2 to capital T. Things are what? 0 multiplied by dt divided by dt, complete dt, its integration will be what? T. From this to this, we are saying that this is the mean value, square of that, dt plus this. Now, this is 0, everyone can see. What is this dt? A is a constant, out. Integration of dt is what? T. Let's do it fast. Integration of dt is what? T. Put limits t by 2 minus 0 and you get t by 2. This dt becomes t by 2, 0 to t by 2. This is gone, plus 0 divided by t under the root. What is this? This is t and t cancelled, a upon root 2. What is a? V0 upon root 2 divided by root 2. The answer is what? V0 divided by 2. Write down result for competitive examinations. This thing and this thing, they are what? Results. Go down like this. And those who can understand fast, those who can understand the whole thing fast, for them it's here. What was the meaning of RMS? RMS, current-wise RMS was the DC, direct current, which produces same heat. For the time being, let's use I. Suppose we need I RMS for the complete cycle. We need this. This IRMS means I square R multiplied by T. This I is something which we need for the complete cycle. If RMS value is I, something we are interested in, then that RMS value represents a DC which will produce this much heat in a resistance R in time duration T. For this portion, there is no current, there is no heat. For this portion, we already know the alternating RMS current, which is I0 upon root 2. This is the DC equivalent. Square of this multiplied by R. But now this current is only flowing for this much time, T by 2. T by 2. This is the answer. RT cancel, square, and you get your I. This is what we need. RT and RT gone. This is I0 divided by, this will become 2, I0 upon 2, or make it 2 root 2 like this. What's your I0? Thing which I am calling I0, The thing which I'm calling I naught, you can take that as what? V naught. And you got your answer. The thing which is peak value of current is basically peak value of voltage. You can put V naught divided by 2. V naught divided by 2. This is the answer. Without integration, this is the basic approach. That's how you should answer it. But now remember, for competitive examination, these things are what? Direct shortcuts. Remember these shortcuts in this form. Now write down full wave rectifier. Now in full wave rectifier, you need to choose your circuit in such a manner that for both half cycles, a current passes through the external load. And how you do that? That's how you do this. This is your primary coil, source, Vs for source, same source. Now, this is your secondary coil. What you did, you connected a resistor like this, and your diodes are present in these arms. Now look what happens. For first half, t greater than 0, less than t by 2. In this portion, this is high, this is low. Now remember something special. This is high, this is low. High, low. What about this? This is the middle point of the secondary coil. Let's call it M. High, middle, low. High, medium, and low. To understand number wise, just to understand number wise, and you can also note like this for your understanding. If somebody says this is 20, this is 10, this is 0. Remember like this. High and low. 20, 15, 10. 20, 15, 10, 6, 4, 3, 2, 1, 0. That's how a drop takes place. Which means what? This is high, this is medium, but in this part, what is happening? This is 20. This portion is high. This portion, you connect it to the medium part. You connected this whole thing to the medium part. So let's call it medium. This is what at lower potential with respect to the left terminal. This is high. This is medium. This is also medium. This is high, this is medium. Now look here, low. This is low, this is medium. Now again it will be helpful number wise. Low means 0, medium means 10, high means 20, medium means 10. There will be some change because of R, but forget about it. The understanding version is that this is high, this is low. This terminal is connected to a low potential point. This terminal is connected to a medium potential point. So, if you look at this setup, you find that this lower diode is in reverse bias, and the upper one, this one, is in forward bias. Reverse means no current. Forward means there will be a current, and let's show that current. Let's show that current in this form. A current is present. A current is present from terminal A to terminal B. Remember in this form. A current is present from terminal A to terminal B. Do one thing before I draw the next T value to capital T. Before that, note down this. But I will complete the whole thing in this setup only, and you can draw two separate figures. Note down this one. For first half cycle, that's what is happening. First diode, upper diode is in forward bias, high low 2010. Bottom diode is in reverse bias, low high 010. Numbers are just for your understanding. Now, for the other half, I will do things in blue. Let's do it here. Let me also draw the same thing again. Well, this is your primary coil. You can draw the left side. This is your secondary coil. Connect the whole thing. Your diodes, and we are discussing T greater than T by 2, less than capital T. Yeah, in this part, your output is input is this, becomes negative. Negative means this is low, this is high. Low, high, and therefore this is low, this is high. And call this medium. Low, medium, high. Again, number wise, you can do the same thing. 20, 10, 0. This is 20, this is 10, call it 10. This is 0, this is 10, call it 10. Same point potential technique, 10, 10, 10. What happens? Your upper diode now is in reverse bias, 0, 10. If it's in reverse bias, there will be no current through it. Whereas the bottom one, 20, 10. That's called forward bias, and therefore there will be a current through it, and the most important thing, current is still flowing from, I hope you can see it, current is still flowing from A to B, from A to B. That means direction of current does not change and is also present in the external load, which gives us an output, in this form. That's your VR versus T. This type of rectification is called full wave rectification. If you understand this and this, then write down yes in the comment box. Write down the statement. Write down the statement. During first half, upper diode is in forward bias. Lower diode, bottom diode is in reverse bias. And therefore current flows from A to B. Current flows from A to B in the external load. To the next half cycle, bottom diode is in forward bias. Bottom diode is in forward bias and upper is in reverse. And current again flows from A to B. And current again flows from A to B. Thus giving us an output signal, which is fully rectified, There are modulations, voltage is increasing and decreasing, but is never negative. It's never negative. It's all the time what? Same. That's how your full wave rectification takes place. Now answer two questions fast before we finish this class. Find out average value of output voltage, and RMS value of output voltage for complete cycle. Average and RMS values of output voltage If peak voltage is V0, if peak voltage is V0. I hope everyone can answer this question. Just give it a try. It's not a difficult thing. You can answer it. From this place to this place, your average is 2V0 upon pi. From this place to this place, your average is 2V0 upon pi. What is this? If I say that average is 10, then what is the total average? 10 plus 10 divided by 2, which is also what? 10. And therefore, average for complete cycle, V output average, at the symbol of average, from T0 to capital T for complete cycle is 2V0 upon pi. And RMS is very easy. Why it's easy? What is RMS of this part? If your output signal was in this form, having a peak value of V0, then you would say that your RMS is what? V0 by root 2. For a signal like this, RMS is what? V0 divided by root 2. Now, when I give you a fully rectified signal like this, and I ask you what is your output VRMS, then during the, if you remember the calculation part which I showed you here, during the RMS calculation we go for square. Once you go for square of this, there is no difference between this and this. So, whatever is the RMS of this is the same RMS for this. Listen again. This is the negative part, but during the RMS process, you go for square, mean, root. When you go for square, this negative also becomes what? Positive. And then there is no difference between this and this. So, we already know RMS of this type of thing, same RMS is valid for this, which means your RMS for complete cycle is V0 upon root 2. VRMS is V0 upon root 2. Well, note down this much and rest will take in the next class. Thank you very much.